So let's go ahead and get started on today's material. So the first thing that we're going to talk about is the ideal transformer. So I want us to look at the following circuit, and this will be a circuit in the frequency domain for what it's worth. So we are going to have some source voltage Vs that is a phasor. And I am going to apply that source voltage to one of the windings of my transformer. And I'm going to use a new symbol here that's going to look fairly similar to the old symbol for what it's worth for my transformer. So I'm going to have a dot on one of the coils and a dot on the other coil. And for right now, we're going to worry about dots on the same side, and we'll sort that out in a little bit. I'm going to put these vertical lines here in between the coils, and I'll talk about what they mean momentarily. Now over here on the right-hand set of terminals, I'm going to apply some load impedance, ZL, like so. All right, so here in the middle, between these sets of terminals, is what we are going to call an ideal transformer. So everything that I've boxed here in red. The voltage drop across the terminals on the left-hand side are what we're going to call our primary voltage. The current that's flowing into our first coil, I1, is going to be our primary current. The voltage drop across the right-hand coil, V2, is going to be our secondary voltage. And the current that's flowing out of the coil on the right-hand side will be I2, our secondary current. Now, I could, if I were so inclined, change the polarity of either of those voltages or change the direction of either of those currents. And sometimes that's going to make a difference, and other times it is not. And so we'll kind of sort that out as we go. Okay. So an ideal transformer is characterized by a few different things. Okay. Let me write down here, ideal transformer. So in an ideal transformer, the resistance of our coils is assumed to be 0 ohms. So we have lossless coils. Okay, so we don't have any at least real impedance associated with them. Our coils will have some inductance. So I'm going to call L1 my primary inductance and L2 my secondary inductance. And these inductances are related to the number of turns that my coils have, which is typically depicted as a ratio. So you might see N1 colon N2 like so. So this is telling us how many turns coil 1 has, that's N1. How many turns coil 2 has is N2. And here in a couple of moments, excuse me. Okay. Yeah. Here in a couple of moments, we are going to relate inductance to the number of turns and give that a special definition. So anyway, in our ideal transformer, the resistance of our coils is 0, and the coupling coefficient of our coils is 1, meaning that we have perfect coupling. That's what those two long vertical lines there actually represent, perfectly coupled coils. So that's a shorthand notation for effectively like, hey, we definitely have an ideal transformer in this particular circuit. Okay.
I just make a lot of sense. It's so ideal to everything, to all wires, R1 or 0.
Yeah. Perfect couple, no losses. So this is the best case you could ever conceivably have. Absolutely. All right. So we learned when we started looking at magnetic coupling that the inductance of a solenoidal coil is proportional to the square of the turns ratio. And so that allows us to come up with the following relationship. So the inductance of coil 2 divided by the inductance of coil 1 is going to be effectively the square of the number of turns in coil 2 divided by the square of the number of turns in coil 1. And we call this relationship a squared, or so this is equal to a squared, where a, the ratio of N2 over N1, or the square root of L2 over L1, is what's called the turns ratio of the transformer. And this is a critical parameter, and we're going to explore it in a moment. So I'm about to derive something, and as part of that derivation, I'm going to be playing around with these relationships. So I want to show you guys something really quickly here. So this is a quick aside thing. I'm not going to expect you to know it. I'm just about to use it, so I want you to know where it comes from. So if we have, bless you. Thank you. The quantity L2 divided by A, our turns ratio, what is that going to look like? Well, that would be L2 divided by the square root of L2 over L1, which is the exact same thing as L2 multiplied by the square root of L1 over L2, or the square root of L1 times L2, which for perfect coupling is nothing more than our mutual inductance term out. Another thing that we can look at is that A squared times L1 would just be L2 over L1 times L1, which just comes out to be L2, so that whenever we see L2, we can just replace it by A squared times L1. All right, so now let's derive a relationship here, okay? So I'm looking back at this particular circuit diagram. And all we're going to do is do the exact same thing that we've done previously. We're going to write an expression for the voltage V1 across that coil in terms of our self-inductance component and our mutual inductance component. And then we're going to do the exact same thing for that voltage V2. Okay. So looking at this guy, let's say that V1, all right, so let's start here. So our self term, I believe, is just going to be J omega L1 times I1. Okay? So I'm saying that because the positive polarity terminal of my voltage V1 is on the same side as the dot. And my current I1 is flowing into the dot. So we're just obeying the exact same rules that we've done previously. Okay. So we would have, excuse me, J omega L1 I1 as my self term. And now we're going to have our mutual inductance. Well, what's the sign on that mutual inductance term going to be? So I believe it's going to be negative because the positive polarity terminal of V1 is at the dot, but the current I2 is flowing into the not dot or out of the dot. So that one should have a negative sign, right? So we'll have J omega L1 I1 minus J omega M I2. Are we all okay with that? All right. So we're going to play around with this a little bit. So J omega L1 I1 is going to stay the same. Now we're going to have minus J omega. So we just found out a moment ago that M could be written as the square root of L1 times L2. So let's put that in here. Like so. We could go on a little bit further and write this as J omega L1 I1 minus J omega A times L1 times I2. So we might need to prove that really quickly. Let's do that over here real quick. I don't know why I didn't have that written down a moment ago. So A times L1 would be the square root of L2 over the square root of L1 times L1. So that's the square root of L2 times the square root of L1. So that is the same thing as M as well. We okay with that?
It might be due to but square root of L1 L2 times, like all you're replacing. We replaced L1. No,
We haven't replaced,
we
we replaced M.
with square root L1 L2.
Mm-hmm.
Then we changed it back into just L1. So we
So-
brought in A, and A, okay, never mind, I'm good.
Good. Okay. Yeah, so just to be clear, L1 could be written as square root of L1 squared if we wanted to, and it would sort out exactly what it's like. So realistically, that intermediate step wasn't necessary. I just didn't have this relationship written down. I was trying to remember where it came from. But anyway, so what we could do here, we now can see, I hope pretty easily, that there is a common factor of j omega L on both of these terms, or excuse me, j omega L1. So we could take that out. So we would have j omega L1 times I1 minus a I2. Anybody got any beef with that? All right. So on the right-hand side here, let's do the same thing for the voltage V2. So let's scroll up and look at what's going on here. All right. So for our voltage V2, the positive polarity terminal is at the dot, and our current I2 is flowing into the undotted terminal. So I believe that we will have a negative sign on our self-inductance term. Absolutely right. So we should have a negative j omega L2 times I2. And now let's look at our mutual term. So our positive polarity terminal, the voltage V2, is at the dotted terminal of coil 2. And our current I1 is flowing into the dot of coil 1. So I believe our mutual inductance term should have a positive sign. So that's going to look like plus j omega M times I1. And now we'll make a couple of substitutions. Okay. So the first thing that we can do is we can replace L2 with a squared times L1. And we're going to do the exact same thing we did a moment ago. So M is the same as square root of L1 times L2, which we also learned is the same thing as A times L1. So let's just go ahead and jump straight to A times L1. And we have an I1 here. Okay. So there is now a common factor of j omega L1 times A that we can pull out of both sides, right? So I would have j omega L1 times A. I'm going to have an I1 from the right-hand term, and I'm going to have a minus a, sorry, I missed the I2 here, my apologies, times I2 for my left-hand term. So are we okay with that? The negative did not drop off. The negative is why we have a minus a I2. So if we look at these and we take the ratio of these two things, the ratio of our voltage V2 to V1 is going to look like j omega L1A times I1 minus a I2 divided by j omega L1 times I1 minus a I2. And we can see that there's a common factor of j omega L1 in the numerator and the denominator. And there's a common factor of I1 minus a I2, which I did not write that 2 there. Sorry. so that the ratio of those two voltages is literally just the turns ratio. Absolutely correct. So that is a fantastic question. So what Baylor asked was, is this result always A, or did it just happen to be A for this case? So if the positive polarity terminal of both voltages is at the dot, it will always be this. If we put the positive polarity terminal of one of them at the not dot, it will come out to be negative A. The direction of the currents is completely unimportant. So anytime we have positive polarity terminals at the dots, it is always A. Anytime one, exactly one of the positive polarity terminals is at an undotted terminal, it's negative A. If you want to mathematically prove that, I'm happy to, but I don't think it's particularly important. All right, so what does this relationship tell us? Well, effectively, it tells us that if we can figure out what the voltage is at either our primary voltage V1 or our secondary voltage V2, we immediately know what the other voltage is because it's either scaled up or down by a factor of A, depending on which one we know, right? So we could say pretty easily here that V2 is simply equal, excuse me, to A times V1, or alternatively, we could say that V1 is equal to V2 divided by A. So in an ideal transformer, knowing one of those two voltages and our turns ratio immediately gives us the other with literally no more work. So now let's figure out what the relationship between the currents might be. And in order for us to do that, we're going to look at power, okay? Excuse me. So if I look at this, excuse me, oh, my throat. If I look at this diagram right here, how I would interpret things is that coil one is absorbing some amount of complex power from our voltage source. And I'm saying that because the current I1 is flowing into the positive polarity terminal of the voltage V1. And then coil two is supplying some amount of power to our load, the L. So that overall, the purpose of this system is for the voltage source Vs to wind up supplying some amount of net power to our load. Our transformer is just there, really converting energy around, making voltages larger or smaller depending on what A is. And as we're going to find out, it's going to have an inverse relationship with the current. And we're going to figure that out by looking at complex power, okay? So I am saying that the complex power absorbed by coil one has to equal the complex power supplied by coil two. Effectively, power in equals power out, or energy is being conserved. For an ideal transformer, it has to obey the law of conservation of energy. So this shouldn't be too wild of a thing. So what is my fundamental definition for complex power? V times I conjugate, absolutely. So that was an RMS phasor voltage V and an RMS phasor current I, right? We're not dealing with RMS phasors here, so I'm going to fix things by literally just adding a factor of 1/2 outside. Okay. So we would have 1/2 V1 times I1 conjugate would be equal to 1/2 V2 times I2 conjugate. Anybody got a problem with that? It's just using our definition, right? So if we take this a step further, we could say that the ratio of I2 conjugate over I1 conjugate would be equal to what? So let's think about things here while we do this algebra, right? So I'm going to leave the I2 on the right-hand side of my equal sign, and I'm going to move the I1 over because I expect to see that in the denominator. So in order to get all of that sorted out, I need to divide both sides by 1/2 times V2. So I'm going to wind up having 1/2 V1 over 1/2 V2. The 1/2s cancel each other out, and I'm left with V1 divided by V2, which is exactly equal to 1 over A. 100% correct. So that is our current relationship, right? So we can say from this that I2 is equal to I1 over A, or I1 is equal to A times I2. Because we're conjugating both the numerator, or both sides, the conjugate is effectively going to wind up going away here. So now that we know how our voltages and currents are going to behave in an ideal transformer, let's look at some interesting consequences of these relationships. Get past all these gross derivations. So let's say that I have the simple system that we described above, where I have my voltage source Vs here's my primary voltage V1, my primary current I1. I'm going to put the dot here. Turns ratio N1 to N2. And once again, my load impedance ZL like so. Here's V2. And here is I2. And just to remind us of things, we know that V2 over V1 is A, and I2 over I1 is 1 over A. So what I'm interested in figuring out is effectively what the impedance that my voltage source sees by having a load connected to my transformer. So let's think about things really quickly here, okay? So my impedance ZL is by definition the ratio of whatever my voltage V2 is divided by whatever my current I2 is. We are going to call ZL prime. This is our reflected impedance. And so I want to say specifically here, we're defining things from reflecting our impedance from the secondary to the primary. Is just going to be the ratio of V1 over I1. Well, we know that we can express V1 in terms of V2 because we have an ideal transform, right? So what would V1 be in terms of V2? Go back to your notes from literally 3 minutes ago. V2 divided by A. All right, so we're going to have a V2 over A in my numerator. What's I1 in terms of I2? A times I2. Okay. So to me, that looks like 1 over A squared times V2 over I2, or simply 1 over A squared times my load impedance. So if I need to refer my impedance from the secondary side to the primary side, I simply divide by the square of the turns ratio. What do you think I would need to do if I wanted to reflect an impedance from the primary over to the secondary? Multiply by the square of the turns ratio. Okay, so we can reflect our impedances back and forth and all of this kind of good stuff. So let's look at an in-class assignment problem. Yes. So for our in-class assignment problem 1, we have the following circuit. We have some source voltage Vs of t. Five ohm resistor. A 15 millifarad capacitor. Here's a 2 ohm resistor. A 20 millihenry inductance. I'm going to put my dot down here. I'm going to define my voltage V1 as my primary voltage like so. My voltage V2 as my secondary voltage like so. My primary current I1 like so, and my secondary current I2 like so, and Vs is equal to 45 cosine 200t plus 35 degrees volts. So I want us to find our primary voltage, secondary voltage, primary current, and secondary current using the relationships that we have just come up with. So I hope it is very obvious to all of you that this problem is currently expressed in the time domain, and we are never going to do math in the time domain for any of these AC circuits. So the first thing that we need to do is to convert this into the frequency domain, right? I'm sorry, what was that? So Vs is 45 angle 35, absolutely right. So let's go ahead and write that down here. It is indeed. So the impedance of my resistor is going to be 5 ohms. What's the impedance of my capacitor going to be? So what's the equation? J omega C. You said that's negative 1/3? Yep, okay, so negative 1/3. So I'm just going to lump those two together as a single impedance. So I'm just calling that 5 minus J 1/3 as kind of my primary loop impedance. Okay. Now we're going to do the exact same thing to our secondary. Okay. So obviously the 2 ohm resistor is going to stay a 2 ohm resistor. But what's the 20 millihenry inductance going to look like? So 200 times 20 times 10 to the minus 3. J4, absolutely. All right. So this is what our circuit looks like in the frequency domain in its most simple form. Let me go ahead and express my phasor current here. So this is I1, and my phasor current here is I2. All right, so we're now trying to sort out what V1, V2, I1, and I2 are. Anybody have any thoughts on how we might do that? Oh, thank you. I didn't remember to write that down, so my apologies. 3 to 5. Okay. So A is going to be what? 5/3. N2 over N1 is just 5/3. And I apologize for not writing that down until now. Okay. How?
We have to. Oh, we can dash something.
We could, but I don't want to. So what would happen if we reflected that 2 plus J4 ohm impedance over to the primary side? Right. So if we reflected that impedance over, what we would wind up having is 45 angle 35 degrees volts. Here is our 5 minus J 1/3 of an ohm impedance from our primary loop impedance. Here is our reflected impedance. And that's the voltage V1 that we were trying to find. When we reflect it over to the other side, that impedance is effectively just taking the role of everything to the right of this dashed line. Okay. So how do we reflect that impedance again? So we take our impedance and we divide it by our turns ratio squared. So that's going to be 2 plus J4 ohms. And then we're going to have a 25 down here and a 9 up here. Anybody got beef with that? Okay. So how would we find V1? It would be. So how could we find that? Voltage division. Sure, absolutely. So 45 angle 35 in our numerator, we're going to have 9/25 of 2 plus J4. In our denominator, we're going to have 5 minus J 1/3 plus 9/25 of 2 plus J4 ohms. And let's throw this in a calculator and see what shakes out. So 45 angle 35 multiplied by 9/25 times 2 plus 4i over 5 minus 1/3 I plus 9/25 times 2 plus 4 I. And I get a stack error, which means I gave it too much complex math. That's why I don't like these calculators. Forgot to bring the other one. Let me sort this out real quick. Store that as A. All right. So A over 5 minus 1/3 I close plus A, multiply that by 45 angle 35. Turn that into order form. I get, looks like I have a little bit of an error, but that's okay. 12.435 with an angle of 87.435. 485 degrees. Okay. So, on the answer sheet that I have 82.458. So it looks to me like I put a 2 instead of a 7 and transpose the 5 and the 8. But anyway, it's close enough to where this makes sense to me. The process is definitely correct. Okay. So just to be clear, how we got here was simply reflecting our secondary impedance over to the primary so that we effectively get rid of the transformer in the circuit entirely because it's now unimportant. We know what impedance is seen across the input terminals, the primary terminals of our transformer, and then we just performed simple circuit analysis there. Okay, so how would we get our primary current I1 from this? So V1 divided by 9/25 times 2 plus J4 ohms. So the voltage drop divided by the impedance gives us the current. Absolutely right. So divide that by 9/25 times 2 plus 4i. I get 7.724. With an angle of 24.050. Again, the angle is slightly different there because this angle was slightly different from earlier. So I'm not too particularly worried about that. Process is definitely correct. How do we get so is it A times V1 or V1 over A? A times V1. So that's just going to be 5/3 times 12.435, which is 20.725. Phase angle is going to stay exactly the same. And how do I get I1 over A? Absolutely. So there's a surprisingly small amount of circuit analysis that is involved once we start knowing what our primary voltage is. Okay. So 7.724 times 3/5 is 4.634. With an angle of 24.050 degrees. All right. Okay, so I think we have impedance reflection down, and realistically, we could do every other problem in this in-class assignment set just doing the impedance reflection and stuff that we've done here. So the rest of this is just introducing other interesting things that we can do having an ideal transformer. And we'll circle back around to some of those problems here in a moment. So let's say that we had the following circuit. Okay. Actually, I want to go back and ask one quick question about this, because this result that we used here is absolutely correct. A times V1. are we sure it's not supposed to be negative A times V1? The positive is by the dot on both sides. So even though I drew dots on opposite sides to try to trip you up, because the positive polarity terminal is at the dot on both sides, it is literally just the A relationship. If I had put the positive polarity terminal of V2 on top, then we would have a negative A relationship to use there. Thanks. So if both of them are on the negative, then we just use A. It's only if one of them is on a negative, or excuse me, if the positive, oh gosh, goodness. So as long, or if exactly one of the positive polarity terminals is on a undotted side, we use negative A, or our turns ratio relationship is negative. Every other case, it's positive. So if positive polarity terminals are both on dots, or the positive polarity terminals are both on not dots, it's still positive A. It's only when one is on the opposite side. Okay. All right, so let's look at Thevenin equivalent relationships. Quit being a baby. I don't know. So So let's say that we had a system that looked something like this. So we have an excitation source VS1 and then some primary loop impedance Z1. And then here is where we're going to put our terminals for our ideal transformer. And I'm going to explicitly label these terminals as A and B. This is the voltage drop across our primary. And this is the current flowing into our primary. Here we have our secondary current, I2, our secondary voltage, V2. Let's call this terminal C and D. And then we have some secondary impedance, Z2. And then a second excitation voltage, VS2, like so. So really, what's making this any different than what we literally just did is the fact that there's a second voltage source, okay? So if that voltage source were 0, this should behave exactly like the impedance reflection that we've already seen. So that's kind of a little bit of a sanity check for us to make sure that we're doing things well. Okay. All right, so based on the polarities of our voltages V1 and V2 and the location of our dots, what should the ratio of V2 to V1 be? A or negative A? Yep, positive. All right. And I2 over I1 should be 1 over positive A. This is just reminding us of the relationships that we're going to wind up using. Okay. So what I want us to do is find the Thevenin equivalent circuit. Looking into terminals. A and B. Okay. So we're going to find a Thevenin voltage looking in, and we're going to find a Thevenin impedance looking in, and then we're going to put those results together to give us our Thevenin equivalent circuit. Okay. So let's start by finding VThev seen looking in to A and B. So I'm going to disconnect that voltage source VS1 and that impedance Z1, and I'm going to be looking into those terminals, right? So our network of interest is effectively just this guy. Here's A, here's B, here's the voltage V1, here's I1, here's C, here's D, here's the voltage V2, current I2, here's Z2, here's VS2. So let me ask you guys a quick question here. What should the current I1 be? I expect you to be able to look at this and tell me. That should give you a pretty strong hit. Oh, and I forgot my dot here. Yes, why? Exactly right. It's an open circuit. So how can there be literally any current flowing through our primary if it's open circuited? There can't be. So it is literally just zero. What does this tell us that our secondary current is? Also zero. Because zero, I2 would be I1 divided by A, right? Well, zero divided by A is still just zero. So there's no current flowing. If there's no current flowing in the primary, there literally cannot be current flowing in the secondary. Okay. So now that we know that there is no current flowing in the secondary, I want us to find the voltage V2, which is the voltage drop across our secondary. So if I2 is zero, there is no voltage drop across that impedance Z2, because 0 amps times an impedance Z2 is just 0 volts. So I believe very firmly that V2 is just our source voltage, VS2. Our voltage V1, which is the same thing as the Thevenin voltage looking into terminals A and B, will then be what? It's not going to be zero and it's not going to be the same. What does the turns ratio tell us has to happen, right? So V1 is just V2 divided by A. So we would literally just see VS2 over A. Now let's find ZThev looking between terminals A and B. So that means I'm going to turn off my voltage source because I'm looking at a dead network. So here's A, here's B, primary voltage V1, secondary, excuse me, here's my secondary voltage V2, B, D. All I'm going to see over here is my impedance ZL. All right. So the Thevenin impedance is the impedance seen looking into terminals A and B. What is it going to be? Forgot to draw this damn dot again. I'm going to scroll back up really quickly. Sorry. What did we do in this problem? Right? We reflected the impedance from the secondary over to the primary. Let me blow you guys' mind really quickly. What if I put an A here, a B here, and a C here, and a D here? It's the exact same thing that we're dealing with. So however we reflected our impedance ZL from the secondary to the primary earlier is the same damn thing we're doing right now. This is literally just a special case of finding the Thevenin equivalent of the network connected to the secondary terminals where the source voltage is 0. So VThev between A and B is literally just ZL over A squared. Because it has to be the exact same thing it was earlier. We're doing the same thing. How can it be different? Okay. So if we put these two results together, our original circuit would simplify to this. So here's VS1. Here's our impedance Z1. Here's terminal A, here's terminal B. Now I'm going to replace everything to the right of terminals A and B with its Thevenin equivalent. Sorry, that says ZL, that should be Z2. It's a single phase thing. We haven't worried about three phase yet. Actually, sorry. This impedance right here should be Z2 over A squared. And this voltage right here should be VS2 over A. This is still, for what it's worth, our primary voltage V1. Show up an hour earlier when you're supposed to. You watch the damn video. All right, so this allows us to effectively convert a circuit where we have something potentially gross on, one side of our transformer or the other into something incredibly simple that we can analyze just using very basic single phase circuit analysis. So without too much math, because you guys are getting bored with it and I know I'm getting bored with it, what do you think would happen if we needed to reflect something from the primary side to the secondary side? What would the Thevenin equivalent impedance looking between C and B, or excuse me, C and D look like? Yeah. So we'd multiply the VS1 by A, and we'd multiply Z1 by A squared. So if we are referring from the secondary to the primary, we divide. If we're referring from the primary to the secondary, we multiply. Nothing particularly difficult. All right. Now, let's talk very briefly about the concept of auto transforms. So when we talked about transformers and introduced the concept of them in our last class meeting, we were talking specifically about, we have two separate coils of wire, right? One of the principal advantages of dealing with two separate coils of wire like that is that we have electrical isolation between the primary and the secondary. They are not physically in contact with each other. We don't have to worry about anything like that. So an auto transformer effectively does the same role as a transformer, but it does not provide that isolation. An auto transformer is formed by literally having a single coil of wire, and then we tap somewhere in the middle of it, and that allows us to have effectively a transformer based thing, but we don't have that electrical isolation. So let me kind of explain what's going on there, right? So we can either have what's called a step up auto transformer or a step down auto transformer. We'll start with a step up. Yes.
I understand stepping down. I just feel like it would have to be such a large. Like it would have to be. I can't look at this and think that it would be simple to step down to a whole other realm of voltage that's usable. It's just using this.
So like it's only dependent on the turns ratio effectively. So if we have a very, very high voltage on one side, we would make sure that that side had a large number of turns. So if N1 is significantly greater than N2, then that means that our secondary voltage will be significantly smaller than our primary voltage. So if we want to step down 13.5 kilovolts down to, let's say, 240 volts, which is what every pole pig transformer in this area is doing, then effectively the easiest, most dumbest way to do this would be to put 13,500 turns on your primary and 240 turns on your secondary, and that'll get the job done. Now, we do have to pay attention to the size of your wires and stuff like that, because the current that's flowing in the primary is going to be significantly smaller than the current flowing in the secondary for a step down transformer, and the opposite will be true for a step up transformer. But from a practical standpoint, it's just literally putting the right number of turns on the primary side versus the right number of turns on the secondary side to hit any achievable voltage. A step up transformer, step down transformer are literally the same thing. Like literally the same thing. It's just, do we put a high voltage on primary side or the secondary side? So, or the number of the side with lower number of turns or a larger number of turns. That's all a transformer is. Probably so. I don't know. So auto transformers, like I said, are doing the same thing, except that we only have one coil. We just have access to either apply or take voltage somewhere in the middle of that coil. Okay.
How is this not like, how is this not a cheat code, not having access to very much voltage and have the series of transformers and boost the.
That is literally what we do. So getting a little bit ahead of things. No, it's fine. Yeah. So getting ahead of things, and this is something that we're going to talk about a little bit on Thursday or whatever, but it's not a big deal. We'll circle back around to auto transformers in a moment. So if we wanted a distribution system, so let's say that we had some RMS voltage that is being provided by a generator. So this might be, this would be at an electrical utility, like generation plant. What do you think the voltages there might be? Usually be on the order of low kilovolts, probably 10 kV to 20 kV, that kind of thing. So if we say that this voltage right here has, our generator is generating a magnitude of 20 kilovolts RMS. If I talk too much about this, we're not having class on Thursday. So here's our 20 kilovolts on our primary side of this. Now we're going to have some transmission lines. They would have some impedance, but for now, let's ignore things. And this is a very simplified representation here. So in our homes, we would have a magnitude of around 240 volts RMS. We split that into plus and minus, that 240 into plus and minus 120, which is what we get on our outlets, but that's another bag of cats. That's just a center tapped transformer type thing. So we have the generation side on the left-hand side, distribution over on the right-hand side. In the middle is transmission, or how we transmit power over long distances, right? So typically speaking, we step that 20 volt or 20 kilovolts up very, very significantly, depending on how long we're sending it and all of that kind of stuff. So this could literally be on the order of like 450 kilovolts RMS. So like the power lines that are going between Monroe and Vicksburg. I don't remember if those are 450, but they're several hundred kilovolts. Why do we step that voltage up so much? So high voltage means that we have extremely small current, right? The larger that we boost that voltage, the smaller the current is that's flowing through those transmission lines. What are the losses associated with a transmission line? We've talked about this. They're I squared R losses. That's just converting current, the resistance of the line, converting current into heat. So the higher that we make our voltage, the smaller our current is, which means the less I squared R losses that we have in our transmission network. So we want to boost that up as high as we possibly can, and we keep it at that high voltage for as long as we can. And then when we get somewhere closer to residential areas, we step it down, usually somewhere in the ballpark of 13.5 kilovolts, 25 kV, something like that. And then when we get to a residential area, we step it down again to stuff that's actually usable by the end user. So this transmission section right here is actually 3 or 4 different step up and step down stages to get it to what we can use. Absolutely. But power in has to equal power out, right? So if we had a very low power thing on our side and we were trying to, send that over a very long distance, we would at a maximum only be able to get whatever power that we were putting in at the out, right? So, but 100% reversible. that's actually one of the reasons, I had a student in my Circuits 2 class last year, or last quarter, asked me about, something that I think his family had purchased off of Amazon. I'm gonna go on a little bit of a rant here, but it's okay. Or a little bit of a rant more so than usual. How many of you guys have seen, there are these cables and they're effectively, they have two male ends on them to plug into a receptacle like this.
Yeah, and it's like,
Yeah. Yeah. Anybody who buys one of those is an idiot and a potential murderer.
Yeah.
So those cables are used to do effectively exactly what you were just talking about. Okay? So you would plug one end of a cable like that into your generator and the other end into an outlet in your home so that you backfeed everything, electricity from your generator into your home. The big problem with that is that if you don't remember to disconnect your main breaker, when somebody's working on the utility lines, you're sending energy to that too, and you could kill a man. So that's why I think anybody who buys a cable like that is an idiot and a potential murderer. These sockets right here are rated for 15 amps. I can tell that literally just by looking at it. If it had, actually, I take that back. This one is a 20 because it has a notch. So that's a 20 amp outlet. The other ones around the room without the little notch are 15 amps. There's all kinds of different things, all kinds of different ratings. I'm not super worried about the current, but if you have a high enough voltage, because if you're getting 120 out of your generator with a large, 120 volts, your generator, let's say, is rated for 2 kilowatts, which would be an extremely small generator, right? What's 2,000 divided by 120? 16, 18 amps, somewhere in that ballpark, right? How much current do you think it takes to kill a man if it flows across his line?
No, it's not a lot.
It's a couple of milliamps.
Yeah.
So if you step this voltage from 120 back up to 13.5 kV, there's still enough current in that transmission line to kill somebody who's actively working. All of that could be prevented if their main breaker was thrown so that their home was disconnected from the utility lines. But a person that buys one of those shit cables isn't smart enough to realize they need to turn their main breaker off to make sure that they're not backfeeding their entire neighborhood. So anyway. They have a disconnect. Absolutely. Yep. Very small. Anything can fail. But so, yeah, when you hook up a generator, like when you have a whole home generator or a permanent generator for your house, it has an automatic disconnect switch. So that's what effectively physically switches your power from being connected to the grid to being connected to your generator. There are two isolated things. And it has to switch back to disconnect your generator back to the grid. So it automatically has that switching in it. If that switch were to fail, the other thing would be permanently disconnected because it's an either or situation, not a both. So you would always be running off of grid power or always be running off of generator power, but they're never intermingled.
So nothing could accidentally go.
Yes. The grid and the generator are never connected together. All right, auto transformers. I mean, I think it's important and relevant. You guys are going to be kind of doing this stuff. All right, auto transformer. Specifically, step up auto transformer first. So from a circuit perspective, we would see something that looks akin to this. So we would have our excitation voltage over here, some resistance R, that's just kind of arbitrary. And then here is our number of turns N2 in our secondary. And then here is N1. I'm going to draw these long lines like this to show that these are perfectly connected to each other, or perfectly coupled to each other. Here's our impedance ZL. And then our primary voltage would be here. Sorry, this is getting busy. And our secondary voltage would be here. So our secondary voltage actually includes our primary voltage because again, this is representing literally a single coil that we have access to a voltage somewhere in the middle. Okay. So here is our primary current I1. And this is our secondary current, I2. Okay. So let's sort some things out here. We're going to sort out what our voltage V1 is. So the positive polarity terminal of our voltage V1 is at the dot for that coil that has N2 turns. I know that might seem weird, but we'll sort all that out. We've got to pay attention and do a little bit of bookkeeping. Okay. So my self term would be J omega L2. So whatever that inductance of that coil is that has N2 turns. What's the total current flowing into the dots for that coil with N2 turns? I1 minus I2 from Kirchhoff's current law, right? I1 is flowing into that node, I2 is flowing out, so I1 minus I2 has to be flowing down. And then we have our mutual term. And so the current I2 is flowing into the undotted terminal of the coil with N1 turns. So we're going to have a minus there, right? So minus J omega M I2. And we can now play around with this a little bit. So we know that L2 is nothing more than A squared times L1 from our previous relationships. So we would have J omega A squared L1 times I1 minus I2. We know that M is A times L1. So that'd be minus J omega A L1 I1. And we wind up getting, sorry, you're right, I2, my apologies. So we could pull out a J omega A L1, and we would have A times I1 minus I2 minus I2 like so. So you see these in a lot of distribution substations. And again, they're used in applications where we don't need electrical isolation between the primary and the secondary because they are literally physically connected together. It's the same coil. So for V2, let's sort that out, okay? So our self term, I believe, is going to be negative because the positive polarity is at the dotted terminal and the current I2 will flowing into the undotted terminal. So we're going to have negative J omega L1 times I2. We have our mutual term, right? So there is a current of I1 minus I2 flowing into the dot for that coil with N2 turns. So that's going to look like plus J omega M I1 minus I2. And then we will have plus, excuse me, V1. Apologies there. And the reason why we have plus V1 is those first two terms are just what's going on for coil 1, but V2 is defined to be the voltage drop over coil 1 and coil 2 together. So now we're going to play around with this mathematically. First thing we'll do is simply substitute in our relationship for V1. So that's going to look like negative J omega L1 I2, where we have M, we're going to replace that with AL1. So this is plus J omega AL1 times I1 minus I2. Now we're going to add V1. So that's plus J omega L, excuse me, J omega AL1 times A I1 minus I2 minus I2. And now we can start lumping things together. So we've got a bunch of I2 terms. We've got a bunch of, so we've got a factor of J omega L1 times A I1 minus I2 minus I2. That's from our first two terms getting put together. Plus J omega A L1 times A I1 minus I2 minus I2. And so I can say that this is J omega L1 times 1 plus A times I1 minus I2 minus I2. So the ratio of V2 over V1 winds out being literally just 1 plus A over A. Let's play around with that a little bit. What happened to this part right here? It's this one right here. So we have 1 plus A over A. So that is 1 plus N2 over N1 divided by N2 over N1. Multiplying both sides by N1 over N1 gives me N1 plus N2 divided by N2. So let's think about this for a moment. What does this represent? N1 plus N2 is the total amount of turns in our single coil. And N2 is just the number of turns we're treating as our primary. So this is just a ratio of the total turns divided by the one that we're looking at. Right? So we have step up. If we had a step down auto transformer, actually, just while we're at it, our current ratio, I2 over I1, is simply V1 over V2, or N2 over N1 plus N2. Literally just the reciprocal of what we had before. Currents behave exactly how we expect them to behave. Now let's say that we had a step down auto transformer. It's effectively the exact same thing that we have right here, except that we're going to replace VS with ZL and vice versa, right? Everything else is literally the exact same thing. Yes, the ratio of the currents should be the inverse of the ratio of the voltages because the power has to be constant. So if we step the voltage up, we have to step the current down in order for energy to be conserved in the system. So in a step down auto transformer is going to look something like this. So this is going to be our voltage V1 this time. And this is going to be our voltage V2 this time. Now, we could do a similar derivation of what we just did. However, I fundamentally do not think it's remotely required. What do you guys just intuitively think? It is literally the reciprocal of what we just had. Right? So it'll be N2 over N1 plus N2. And our currents will be N1 plus N2 over N2. No derivation required. Why would we need it? It's literally just the exact opposite configuration, so we should expect the exact opposite relationships. All right, we only have 10 minutes left of class, so I would like it if you guys took a crack at in-class assignment problem 3.